Hi, my name is Or Fisher, and today I'll talk about our work, Constant Round Spanners and Shortest Path in Congested Clique and MPC. This is joint work with my co-authors, Michal Dori, Seri Khoury, and Dean Leitersdorf. So first I'll give a brief introduction, some definitions and motivation, and next I'll discuss our algorithms. So our work focuses on two models, the congested clique and the MPC. In this talk, I'll only talk about the congested clique. So what is the congested clique? It's a synchronous communication model in which we have n nodes. Every node may talk to every other node up to log n bits in each round. Their task is to solve some graph property, which in this work is spanners in all pairs shortest path. And their goal is to do so in a minimum number of rounds. So what is a spanner? A spanner is a small set of edges that approximately maintains the distances of the original graph. So let's take an example. So here in this graph, the red edges form a two-spanner on the entire graph. And we see this because for any edge in the graph, there is a path of at most two that spans this edge. Meaning if we have some path of length L, we have a path on the red edges of length at most 2L, meaning the distances are approximated by a factor of 2. And some good parameters to think of when talking about spanners is for any k size order of n to the 1 plus 1 over k, an approximation of 2k minus 1. And this is good parameters because this is believed to be tight up to a conjecture by Erdos on girth of extremal graphs. So as hinted before, we can define the spanners alternatively, not on distances, but on edges. So a set H is an alpha spanner if for any edge we have a path on the spanning graph which is of weight at most alpha times the weight of the original graph. And one easy lemma you can derive from this definition is that if you have a graph and split it in two and compute an alpha spanner on each graph and combine and take the union of these spanners, then this union is an alpha spanner on the union of the graphs. So let's talk a bit about the landscape of complexity in the congested clique. So we know several problems can be done in order of one. For example, MST, which was shown first randomly and then deterministically, approximating the girth, delta plus one coloring, and there are several other problems as well. On the other hand, in shortest path related problems, we're close, but we're not quite there. So you can 1 plus epsilon approximate a single source shortest path in polylog n rounds. You can 2 plus epsilon approximate the all pairs shortest path in polylog n rounds. And you can compute an order of k spanner with a good number of edges in order of log k rounds. So can we achieve for these problems in order of one algorithm as well? Or is it bounded above order of one? So the problem in the congested clique is that we can't really know until we have an order of one algorithm. And the reason for that is any lower bound can be translated into a circuit complexity. And we're very far as the TSS community from solving these problems, meaning that lower bounds are very, very unlikely until major breakthroughs are done. So therefore, the only way to be certain that an algorithm about the right complexity of an algorithm is to get an order of one algorithm for this problem. So so what can we say? So first, there is some sort of natural barrier that occurs when trying to design congested clique algorithms, in particular order of one algorithms, which is the locality barrier. So there is a common technique in the congested clique called the graph exponentiation technique, which takes informally takes a T-round algorithm in the local model and translate it, if it has good properties, to a congested clique algorithm with an order of log T round algorithm for this problem. And informally, it does this by if you can collect at the ith round relevant information from the 2 to the ith neighborhood. And both the work of Doreen Parter and Parter and Yogev for all pair shortest path and spanners respectively use this technique. The problem is for 2k minus 1 spanners with an optimal number of edges, it can be shown that you need omega of k rounds in the local model. Meaning if we use this technique, then we can't get better than the order of log k regime. And we would like something which is order of 1, so we can't really use this technique. So can we hope for better? Because for several problems in this model and in the MPC model, several problems might be considered tight on the locality barrier. And in this work, we answered that yes, for spanners in all pair shortest path, we can overcome the locality barrier and get order of 1 algorithms. So more formally, we show an order of 1 round algorithm for the following problems in congested clique and linear space MPC. We show an order of k spanner with order of n to the 1 plus 1 over k edges in unweighted graphs. Taking k equals log n, we can get a log n spanner with order of n edges, and by propagating it to all the nodes in the graph, we can get an order of log n all pair shortest path algorithm in unweighted graphs, also in order of 1 rounds. In weighted graphs, we get an approximation on our spanners of order of k log n. And again, taking k equals log n, we can translate this this result into an order of log squared n approximation all pair shortest path algorithm in weighted graphs. And this is a speed up of between polylog n and polylog log n, depending on the problem, compared to previous results. So next, I'll discuss our algorithm for computing spanners in unweighted graphs. We'll focus on k equals log n, meaning we would like a linear size spanner with order of log n approximation in order of 1 rounds. And this will also give us the result for order of log n approximation for all pair shortest path in also order of 1 rounds. So our algorithm is based on 2 tools, vertex reduction via hitting set and sparsification. So first, I'll discuss the vertex reduction technique. And as a warm-up, first let's only consider graphs which are roughly d-regular, meaning the degree is between d and 2d. So what is a hitting set? A hitting set is a set of vertices such that every node in the graph has a neighbor in S. So in this example, the black vertices are a hitting set on the graph because every vertex has a neighbor to a black node. And it can be shown that if G has a minimum degree D, then there is a hitting set of size order of n over D times log D. And furthermore, this set can be found fairly simply using a simple random sampling procedure. So how does the vertex reduction technique work? So first we find the hitting set S, and we said that S is roughly, ignoring polylog values, is n over D. So the black nodes again will be our hitting set. Now every node V chooses a neighbor in S, and we form sort of stars where the center of each star is a node of S, and the rest of the star is the vertices that chose S. Now, for each such star, we contract it and solve the problem on the contracted graph. So in this new graph, the size of the vertices is roughly n over d, and the size of the edges is, since we didn't create any new edges, it's still a order of n times d. So next I'll talk about our sparsification technique. Kohonen and Nowicki, each in their paper, showed the sparsification technique for the MST problem, which informally says this: given a subgraph with n vertices and m edges, you can get a subgraph in order of 1 rounds with n vertices, square root of m n edges, that preserves the MST, and they do this deterministically. So in our work, we show a stronger but randomized variant for spanners. What we show is this: given a subgraph of n vertices and m edges, we can find an order of log n spanner with n vertices and m to the 1/3 times n to the 2/3 edges. So how does this help us? Let's consider what happens if we first apply the vertex reduction technique and then apply the sparsification. So first we reduce the graph to roughly order of n over d vertices, and the number of edges is order of n times d. And after sparsification, if you calculate it, this gets you order of n over d to the 1/3, which is order of n. And moreover, if we now take our contracted graph and decontract it, so for every star we decontract the graph, we make it a star again, and take the edges of the star into the spanner, we get an order of n edges, and we will get an order of log n approximation in total on the graph. So how does the sparsification lemma work? First, we split the vertices randomly to d to the 1/3 sets, uniformly at random, v1 up to v to the d to the 1/3. Next, for any pair of sets vi, vj, we send the edges between these two sets to a unique vertex. Then each such vertex locally computes a linear size spanner on the edge set it received. And finally, we merge the spanners together to obtain a spanner on G. So let's analyze the congestion of this protocol. We note that each vertex receives, since there was d to the 1/3 random sets, it receives roughly m to the m over d to the 2/3, which is order of n edges. And also, as we saw, the total number of edges of sparsification is also order of n. So this was an expectation, and there is some dependency between what the nodes receive, but we overcome this in the paper using Chernoff with bounded dependence. So we saw how these two tools work and how can we combine them to get an unweighted algorithm, but this was under the assumption that the graph is roughly deregular. Now we remove this assumption. So what do we do in general graphs? We split the graph into order of log n graphs according to some bucketing of the degrees. So we split the graph, we apply the vertex reduction and sparsification on each such graph in parallel, and finally we merge the spanners back into one. So next, let's analyze how many edges do we have in the final spanner. So recall that since the hitting set was of size n times log d over d for roughly d regular graphs, the graph GI has roughly n times I over 2 to the I vertices, and after the sparsification step, it has only roughly n times I over 2 to the I over 3 edges. Therefore, if you do the sum, the total number of edges in the spanner is order of n. And therefore, you can propagate the spanner to all of the vertices in order of 1 rounds and also solve the all pairs shortest path problem. Next, we'll turn our attention to weighted graphs, where we show to compute an order of n size spanner, with an order of log squared n approximation factor. Let us consider the following simple procedure. A standard assumption in the congested clique is that the weights are integers between 1 to poly n. So we split the graph into a order of log n graphs according to edge weights in the following manner. So the first graphs have weights from 1 to 2, then the second graph from 2 to 4, etc. So we have our log n graphs, and on each such graph we compute an order of n size spanner and merge the spanners together into one single spanner. So this will give us an order of log n approximate spanner. The problem is that the number of edges in the spanner is order of n log n, which is too large for us since we wanted a linear size spanner. So next, our goal will be to reduce to n over log n vertices and only lose a small approximation factor, hopefully something in the order of log n or better. So here's our solution. First, we compute an MST on the graph. Next, we split the MST into shallow subtrees, and each subtree we contract into one node. We compute a spanner on the contracted graph. And finally, we output the spanner plus our MST as the final spanner. And in the paper, we showed that, so this reduces into n over log n if we take the subtrees to have at least log n vertices inside them. And we show in the paper that we only lose an order of log n approximation factor. And this can be shown using very elementary properties of MST, such as the red rule. So finally, let us recap and discuss open problems. We've seen algorithms for spanners in the all pair shortest path problem, where in unweighted graphs we solve for spanners in order of k approximation algorithm with order of n to the 1 plus 1 over k edge set size. And for weighted, we've seen an order of k log n approximation with order of n to the 1 plus 1 over k edge set size. And for the all pair shortest path problem, we've seen an order of log n and order of log squared n approximation for unweighted and weighted graphs, respectively. So what are the open problems? First, our algorithm gives for weighted graphs a order of k log n approximation. Can we find weighted spanners with the order of k approximation in order of one round and the same edge set size? Secondly, one can hope for a better trade-off in constants. So currently we find an order of k approximation in unweighted graphs, but existentially you can show that there is a spanner of size of approximation 2k minus 1 with the same edge set size. Can this be found in order of one rounds? Thirdly, our algorithm is randomized. Can you de-randomize it? So actually, thanks to a suggestion by an anonymous reviewer, that there is a very promising and simple way to do so, and we're currently looking into the details of that. And finally, one hopes to find more problems with the order of one round complexity in the congested clique, and namely MIS and maximal matchings would be great problems to add to that list. So thank you, and enjoy the rest of the conference.